we were looking at thermal expansion of materials last time, and in that we had understood the principle of linear expansion. It's seen that any length parameter changes with temperature according to the principle that fractional change in length is equal to coefficient of linear expansion multiplied by change in temperature. Where the quantity alpha was the coefficient of linear expansion. Delta T was change in temperature. Delta is the change in length, delta L, and L is the original length. So another way of expressing this formula we had seen is that if the length is L naught at some original temperature T naught and changes to LT at some temperature T, which is T naught plus delta T, then delta L by L is equal to alpha delta T, means that final length minus original length divided by original length, that's the fractional change, is equal to alpha into final temperature minus original temperature. So this equation can also be expressed in this way, that the new length at a certain temperature T is equal to the original length at T naught into 1 plus alpha into the temperature difference. So this here is another way of expressing the same formula as the one above, that fractional change in length is equal to alpha into delta T. So this is what we had seen in the previous lecture, which was the first lecture of Heat and Thermodynamics. Now we'll continue from this point today. Apart from this, of course, we had seen temperature scales, etc. All right, so let's start with another example problem. Yeah, no, last lecture notes. Okay, I've sent it on the group. It's there on the lecture notes as well as the recording is there on the group. However, I'll just go through the notes once more if you like. Okay, good. Got it, nice, in the WhatsApp group. Okay. Right, so let's come back to another example problem. We had done one example problem last time. Let's pick up another example problem. Now, this is an important type of problem we are discussing from JEE point of view. Next. Okay. So this will involve calculation of error also. Okay, so let's understand how that happens. So first of all, we have a metallic scale. Okay, calibrated at a temperature of 5 degrees C is used to measure length. Its calibration is nearly perfect with a least count of 1 millimeter at T naught equal to 5 degrees C. So nearly perfect means it's not having any error. And least count, as you know, is the smallest division on the scale. So that's equal to 1 millimeter at a temperature of 5 degrees. Okay. So now this scale is used to measure the length of a wooden plank. To be L naught equal to 400.0 centimeters at T naught equal to 5 degrees. Next, the same measurement is repeated at T equal to, let us say, 45 degrees C. Okay. Alpha for metal of the scale is equal to 8 into 10 raised power minus 6 per degree C. And alpha for wood, let's say, is 2 into 10 raised power minus 5 per degree C. So first of all, to find the true value of the plank's new length at 45 degrees. The least count of the metal scale and the percentage error in a measurement by the scale due to its own expansion. So I'll explain what this means. So what is happening is that the metal scale was calibrated. That means the divisions were marked at a temperature of 5 degrees C. So it was marked accurately with the least count of 1 millimeter at 5 degrees C. But at a higher temperature like 45 degrees C, the metal scale itself has expanded. So the divisions have got wider, slightly wider than the actual value they should have been of 1 millimeter. So if you are using the scale to make a measurement at a different temperature other than 5 degrees C, then there will be some error in the measurement because the scale's divisions are not correct. The least count is not going to be 1 millimeter at any other temperature. So when the temperature is 45 degrees C, we have to calculate the percentage error in the measurement which the scale is, the measurement we are going to make using the scale. Okay. And from that, we have to calculate the measured value not the true value, but the measured value of the Planck's length. And at 45 degrees C, using the given metallic scale. Okay. And in fourth part, we will compare the values of part 1 and 3 and show that the percentage error is same as part 2. Okay. So try out this question. The basic, this thing that we'll use, the basic formula that we'll use for thermal expansion will be the same. Delta L by L is equal to alpha delta T, or the new length at any temperature T is equal to length at temperature T naught into 1 plus alpha into T minus T naught. But along with that, now we have to also use the concept of error propagation that we have seen in the chapter of UTM, units, dimensions, and measurements. So just try this out, people will discuss. Okay, let's understand this question in detail. So there are two things which are expanding. One is the metallic scale itself and the other is a wooden plank. Okay, so let's understand this thing. So our metallic scale, suppose it has divisions made like this. So it has a least count equal to 1 millimeter at a temperature of 5 degrees. And then we have our wooden plank, which whose length we are measuring, and that length comes out to be let's say L naught. Again at T naught equal to 5 degrees. Now at a new temperature at T equal to 45 degrees C, that is T naught plus delta T. So delta T will be 40 degrees C. So first of all, the plank's true length, say LT, would have become LT naught into 1 plus alpha of wood into T minus delta T. Okay. So it would have become 400 centimeters into 1 plus, now alpha of wood it's seen above was given to us as 2 into 10 raised by minus 5 into the temperature change of 40. So the true length has become 400 plus this much. So it has become 400.32 centimeters. This is what the true length of the blank has become. Okay, so this plank is expanded to this much. Okay, but now what happens? The scale also expands. Okay, so secondly, we'll see that at T equal to 45 degrees C, the least count of the scale that actually becomes 1 millimeter into 1 plus alpha of the metal into delta T. So it becomes 1 millimeter into 1 plus 8 into 10 raised by minus 6 into 40. becomes this much. Okay. So you can see that the percentage error is going to be this factor converted into a percentage. So because of the thermal expansion of the metal scale, so any measurement using the scale will have a percentage error of 0.032% at 45 degrees. Okay, so hope this concept is clear over here. Hey, Ganesh, the point is the least count of the scale, no? That is 1 millimeter. So the question is asked us to find out how much the least count is going to give us an error because of the expansion. Because the smallest division, that is called the least count, it is supposed to be 1 millimeter. But instead of 1 millimeter, now it's slightly greater than 1 millimeter. So that is why it is going to give us an error. No? Actually, you're talking about the alpha. No, see, alpha is independent of what scale we use for the length. No? Because alpha is the unit of alpha is per degree C. See, if you see the value of alpha, no, alpha is delta L by L into delta T. So delta L by L is a unitless quantity. No? That's why alpha is expressed in per degree C or per Kelvin. So it is independent of the unit of length that we are using because fractional change in length is equal to alpha into delta T. Now fractional change is independent of unit. No? Is it clear, Kanish? Okay. Yeah, now Prince, see what is happening. That the scale that we have, the calibration of the scale is like this. There are markings made. Now the smallest division is called the least count. So the least count is equal to 1 millimeter exactly at 5 degrees C. But the scale expands. So as it expands, the divisions come a little further apart at the new temperature. So the least count becomes 1 millimeter plus some delta L at 45 degrees C. So that delta L is inducing the error. You understanding? So what is supposed to be 1 millimeter is now actually a little bit longer than 1 millimeter. So that means any measurement using this scale will have some error. Okay, and that error will be of 0.032%. Okay, in terms of percentage error. So we'll just show that using the third part. Okay, so in the third part, what is happening is that 328. No, why 328 beta? It is 3. Okay, that is alpha into delta t. No? See, the metal expands, and the metal expands according to this formula. No? Any length portion of that metal at the new temperature will become the original one into 1 plus alpha of the metal into delta t. This formula. So portion of 1 millimeter would have expanded to this value now. Okay, and alpha for the metal is given as this, and change in temperature from 5 degrees C to 45 degrees C is 40 degrees C. So this value is coming out like this. So you can see that what was supposed to be 1 millimeter, the least count, which was supposed to be 1 millimeter, now the least count has become 1 millimeter into 1 plus 3.2 into 10 raised power minus 4. Okay. So the error has become 1 millimeter into 3.2 into 10 raised power minus 4, because the least count has increased by a factor of this much. So the percentage error has become the error divided by the value of the error into 100. Yeah, we can find, but it's not necessary because I just want to find the percentage error. So that is this. Understood now? Okay. Now let's come to the third part. So now the Planck's true length, you've seen that has become sorry 400.32. Okay. But the scale's least count, or you can say one division of the scale now, has become 1 millimeter into 1 plus alpha of metal into delta t, which we saw as 1 millimeter into 1 plus. Okay. So therefore the measurement, the measured length using the scale, let's say L prime, will be the true length divided by the least count. So the true length is this much, whereas the least count, I'll just express it in the same unit. So I'm making it 0.1. Okay. So this is the measured value. In millimeters, because the divisions are millimeter wise. Okay. So now see, what we can do is we can use a bit of approximation. So alpha of wood into delta T into 1 plus alpha of metal into delta T to the power minus 1. Now we can use binomial approximation. We can bring this power inside. Since alpha delta T is very small compared to 1, we can bring that power inside. So this becomes okay. Now further, this fourth term that we have here, this term, this will become negligible because its order of magnitude is 10 raised power minus 11. So we'll neglect that term and we'll say that L prime is 4000 into 1 plus alpha of wood minus alpha of metal into delta T in millimeters. Okay. Or we can say in centimeters. So L prime becomes 1 plus. Now remember, alpha of wood was 2 into 10 raised power minus 5 per degree C, and alpha of metal was 8 into 10 raised power minus 6 per degree C. Or we can write this as 0.8 into 10 raised power minus 5 per degree C. So we'll write this as 2 minus 0.8 into 10 raised power minus 5 into the temperature difference, which is 40, okay, in centimeters. This is what the length will become. So this is the measured value of the length. So this will be the measured length. Okay. So now see the true length. But the measured length, the error therefore the percentage error okay, and you can see from above when we round it off to a second place of decimal, it agrees. So this is how we can show that the scale is making a 0.03% approximately error in measurement because it has expanded from its calibration temperature to the new temperature of 45 degrees C. It has expanded by a certain amount. So whatever measurement we are making using that scale, it will have a percentage error of about 0.03%. Yes, Ansh, the measured length is of the plank only. So क्या हो रहा है ना, see, the plank has expanded to a true length of L. Its actual length is L, but then we are using the scale to measure its length, and the scale is faulty. So the scale is measuring some value which is the true length divided by the least count of the scale. So the true length is that value. It is L naught into 1 plus alpha of wood into delta T, because it's at 45 degrees C. But the least count is also faulty. Na? It is 1 millimeter into 1 plus alpha of metal into delta T. Okay. So that is why L prime is not the same as L, because this is the value of L. But we are not using a scale whose least count is 1 millimeter. We are using a scale whose least count is slightly greater than 1 millimeter. So it ends up measuring a lesser value. So you can see that L prime comes out to be only 400.2 centimeters, whereas the true length was 400.32 centimeters at this temperature. So why L prime is coming out to be less than L? Because the scale itself has expanded. Is the point clear, Ansh? Okay, very good. Okay, next we'll look at another very important aspect of linear expansion, and that is the case of the change in time period of a pendulum. Okay, I'll show the previous question once more. Okay, finish writing this, then we'll move to the next part. So the next part we will see how the time period of a pendulum changes because of change in temperature and therefore change in length. Okay, so let's look at the next part of thermal expansion. So the change in time period of a pendulum, because its length might change as a result of thermal expansion. So if we have a typical pendulum like this, we know that time period for oscillation as the pendulum oscillates, it has a definite time period which depends on two things, as you know, the acceleration due to gravity and the length of the pendulum. So the time period is given by the formula 2 pi under root L by G. So if this is a metallic wire, so then you can see that at a temperature of T naught, so the time period, but at a temperature of T naught plus delta T, where alpha is the coefficient of linear expansion for the metal. Okay. So the new time period, now if you compare this and this, you can see that okay. Now this is where again we can bring in binomial approximation. So time period at the new temperature of T naught plus delta T becomes into this factor. So you can see that the change in time period has a fractional value of half alpha delta T, or the percentage change in time period is half of alpha delta T converted into a percentage. And this can be understood directly from this fact that time period is proportional to square root of length, and delta L by L is alpha delta T. So obviously delta T by T will be half of delta L by L. Okay, so you can just remember it by this simple logic. The propagation of error concept. Okay. This comes from the idea that if y is proportional to x to the power n, then delta y by y will be n times delta x by x. Okay. So this is an important formula to remember, that for a pendulum, the fractional change in time period is half of alpha delta t when the temperature changes by so much. So make a note of this first of all. Yeah, Prince will understand this with a numerical example, then it will become clearer. Now, this formula you're supposed to know from before, the time period formula. The time period of a simple pendulum is 2 pi under root L by G. Okay. So now you're just applying the thermal expansion formula to the length. So the length changes from L naught at temperature T naught to L naught into 1 plus alpha delta T. So now if you compare this expression with this one, compare these two expressions, just divide them. Divide equation 2 by equation 1. You will get this relation. Equation 2 divided by equation 1. You will get this relation. T by T naught is this thing divided by this. Right? So that's how we get this. Clear enough, Prince? Now we are using the binomial approximation. This step here, the power coming inside, this is the binomial approximation step, where we use the relation that 1 plus x to the power n can be approximated as 1 plus nx if x is small compared to 1. So that's this step. Okay. So in conclusion, we can just briefly remember the concept from this idea here. That time period is proportional to L to the power half. So fractional change in time period will become half of delta L by L because the power is half. So in error propagation, the power comes as a coefficient. This concept. Okay, Ansh, have you finished taking this down? Okay, so let's look at a numerical problem based on this. Okay, okay. Okay. So next, let's look at this example. So a pendulum clock measures time with 100% accuracy at a temperature of 20 degrees C. Okay. Now, if the metal of the pendulum has a coefficient of thermal expansion of 6 into 10 raised power minus 6 per degree C, find the percentage error in the clock's measurement of time at a temperature of, let's say, 60 degrees C. And will the clock be losing time or gaining time? Find the time lost or gained in seconds per day. So the clock is operating instead of 20 degrees C, if it's operating at 60 degrees C, then per day how much time will it lose or gain, depending on whether the clock is running faster than actual time or slower than actual time. So just try out this question, we will discuss. Okay, so people, let's continue with this. Sorry, I had got disconnected. So anyway, let's continue ahead. So what we'll see is that the percentage error in the measurement of time will be, now since delta L by L is going to be this much, 6 into 10 raised to minus 6 into temperature change of 40. Therefore, so the time period increases by 0.012%. So if the time period becomes more, it's correct, Tantrish, what you said, the clock will lose time. So the time period increases. That means the clock will lose time or will run slow. So third, the pendulum is taking longer to oscillate now. Therefore, the clock is slower. Length expand किया तो time period increase हो गया ना अंश. So that means each oscillation is taking longer than it is supposed to take now. So suppose it's a seconds pendulum, it's supposed to oscillate once every 1 second, but now it's taking longer than 1 second to oscillate. So it's recording time slower now. Understood? Okay. So in one day or 24 hours or 24 into 60 into 60 seconds, the clock loses 0.012% of one day. Yes, if it runs faster, that means it's gaining on time now. So the clock loses about 10.36 seconds per day. Okay. So if it continues at losing time at this rate, then you can see that within a week, it will have lost more than a minute of time. So it will be running slower than the real time by more than a minute. in 1 week's time. So it becomes a significant effect. Okay. So hope this question is clear to all of you. So this is an important type of question for JEE level problems. The clock losing or gaining time according to whether the time period is increasing or decreasing. Okay, finished, Prince. Okay, next we will move on to the concept of surface and volume expansion. Okay, so we have a certain surface area. Okay. Then the surface area expands according to this formula, or area at temperature T is area at temperature T naught into 1 plus a certain coefficient beta into temperature difference, where beta is called the coefficient of surface expansion. Now, for any material, the value of beta will be twice the value of alpha. So whatever the coefficient of linear expansion, the coefficient of surface or area expansion is double of that. You know, this is very easy to understand why this is the case. We will look at the proof of this also. So the reason for this is, suppose we have a surface. Now this expands. you can see that L will be L naught 1 plus alpha delta t. The width will also expand according to the same value of alpha, because both length and width are this thing, they are linear dimensions. So therefore area, so if you compare this, you can see that the new area has become, okay, now binomial approximation. So you can see that beta is twice of alpha. Okay, so this is the concept of surface expansion. Now, likewise, the three-dimensional volume of an object also changes according to the principle of volume expansion. So, likewise, the coefficient of volume expansion is 3 times the value of alpha for a given material, because volume is, say, length into width into depth. Okay, so that same concept. So gamma becomes 3 times alpha. Okay, so people, with this we come to a conclusion for today's lecture. Now, based on this, you can do questions from H.C. Verma, okay, volume 2, chapter called Heat and Temperature. Plus, you can also do questions from module 3, thermal expansion. Okay. Just leave out questions for the concept of thermal stress. Okay. And Young's modulus of elasticity, because this particular aspect we will study after doing properties of matter. This we will do in properties of matter later. So other than questions involving thermal stress, you can complete all questions related to thermal expansion. So next lecture we will discuss, it's module 3 now. Heat and Thermodynamics is in module 3 physics, I think. Let me just check for you for a moment. Yeah, it's module 3 only. Okay, so we will discuss some questions in the next lecture, and we'll also start with the next chapter, which is calorimetry. So calorimetry is about specific heat capacity, latent heat, etc. So it's a continuation of things you would have done in 9th, 10th related to heat and thermodynamics also. So that's it for today's session. People, wish you all the best.